Alright, 13.4, we're going to look at ways of expressing concentration. These should all be a review from last year, so we're going to run through these kind of quickly. First, we have a quantitative or qualitative. Okay, you could express a concentration as a quality, say things like it's concentrated, or it's darker, or it's lighter, or it's more dilute, or it's less dilute, things like that. A quality, or we can have a quantity. We're going to look mostly at quantities here. You know, things like mass, liters, some kind of number. What's my molarity, my molality, my parts per million, parts per billion, that kind of stuff. Okay. Now, some commonly used expressions for concentration, and I named a bunch of those there. We have molarity, molality, mole fraction, mass percent, and then parts per million and parts per billion, which are very similar to a mass percent with a little bit of a change in the end there that we'll look at. Okay, so I'll start off first with mass percent. Okay, mass percent is just what it sounds like. It's the percentage based on the masses. Okay, you take the mass of the compound divided by the total mass of your solution times 100. Okay, and we have done this many times before. All right. You can also then look at these percentages in terms of so many parts per million or so many parts per billion, because a mass percentage is kind of like a parts per 100. Okay, because you're multiplying by 100. So if you got a parts per million or parts per billion, these are usually saved for environmental issues with how many parts per million of pollution are there in a river or things like that. Okay, all you do is you take the mass of the compound, divide by the total mass of the solution, it's the same thing, but instead of times 100 for a percentage, you take it times 10 to the 6th, because a 10 to the 6th is your million. That's going to be so many parts per million. And if you look at 1 part per million, okay, or ppm there, that's going to be 1 milligram per kilogram. Okay, because it's so many milligrams per liter of solution, and a liter of solution is a kilogram, because when we look at those. Okay, then if you've got parts per billion, same thing, but now in the billions. So I take the mass of my compound, divide by the total mass of my solution, times 10 to the 9th, and here you are looking at so many micrograms per kilogram. And micro is that kind of U-looking thing with a tail. Okay, that's not the world's greatest. Right there. It looks a little more usually like that. Okay, that's micro. So many micrograms per kilogram, or 1 microgram in a kilogram, that's a part per billion. Okay, so those are all dealing with percentages, or so many per an amount. Okay, so let's look at an example here. I have a solution that's made by dissolving 13.5 grams of glucose, which is a type of sugar, and 0.1 kilograms of water. What is the mass percentage of the solute in the solution? And then we're going to have another one with parts per billion, or I'm sorry, parts per million. So look at A here. I want a mass percent. So if I want a mass percentage, that means I'm going to have the mass of my compound. So 13.5 grams, because that's my solute. Okay, in 0.1 kilograms. So the problem you've got here is you do have to have the same unit. So if I've got 0.1 kilograms, okay, that's the same thing as how many grams? Well, there are 1,000 grams in a kilogram, so you move it over 3 places, and that's the same thing as saying 100 grams. But it's not just over 100 grams, because the entire solution. This is just my solvent, so I've got to add to that, which people often forget, is the 13.5 grams from before, from my solute. Okay, so then I add them together, so it's 13.5 over 113.5. Take it times 100 to get your percentage, and we will get 11.9%. All right, let's look at the next one with parts per million. Okay, so that 2.5 gram sample of groundwater was found to contain 5.4 micrograms of zinc ion. What is the concentration of the zinc ion in parts per million? So if I want parts per million, okay, I take my mass divided by the total times, now I want a million, it's going to be 10 to the 6th. All right, so my amount of grams I have here is 5.4 micrograms. Okay, and in micro, okay, that is 10 to the 6th. So there in 1 gram, there's 1 times 10 to the 6th micrograms. So if I have 5.4 micrograms, we divide by 1 times 10 to the 6th, and we will get 5.4 times 10 to the negative 6th grams. Okay, they get divided by my total. In this case, 2.5 grams is my entire sample, so I'm not adding the 5.4 micrograms to that one. But 5.4 micrograms, if I added that, wouldn't make much of a difference anyway, but you don't add it because that is my total sample. And so then I take this times 10 to the 6th, because I want it in parts per million, not in like a parts per hundred or a percentage. Okay, and I'm going to get 2.2 parts per million. Okay, the next kind of example for some concentrations is mole fraction, molarity, and molality. We had these all last year. Mole fraction is a fraction of moles. It's the moles of your compound divided by our total of the compound. It doesn't have any units. It's percentless. You're not taking it times 100, and it's always going to be between 0 and 1. So you'll get a mole fraction of like 0.68 or 0.72 or 0.34, whatever. Okay, this is a mole divided by a mole. There's no units. Okay, molarity, all right, is the most commonly used one, and that's an uppercase M. So many moles of solute per liter of solvent. All right, if you look at your green sheet, most of these are on your green sheet. Okay, we have molality, which is moles of solute per kilogram of solvent, versus moles per liter, which is molarity. Okay, molarity is the uppercase M, molality is a lowercase, usually italicized m. Now there are some differences between molarity and molality. Okay, molarity changes with temperature. Molality does not change with temperature. Molarity changes with temperature because it has liters in it. Well, my volume is going to change as my temperature changes. So if you're doing an experiment with a lot of temperature changes, you really don't want to use molarity. You'd much rather use molality, which is why they have molality. Okay. You can convert between the two, molarity and molality. All you need is density. Okay, and you'll see a little diagram there on your paper. Okay, and showing you how you convert between all of these. Well, if I have my mass of my solvent, okay, I can then also use my mass of my solution. I can use density then to get my volume, and I can have molarity. If I have my mass of my solute, you use molar mass to get your moles. If I have my moles, I can use either molarity or molality, one or the other. Okay. Yeah. All right, so let's look at an example. Okay, a solution is made by dissolving 4.5 grams of glucose in 25 milliliters of water. Calculate the molality of glucose in the solution. Water has a density of 1. So molality, lowercase m, is moles of solute per kilograms of solvent. Not the whole solution, but the solvent itself by itself. Okay. So I want my moles of solute. Well, my solute is the 4.35 grams of glucose because that is in the smaller amount. I need moles, so I gotta divide by my molar mass. So you add up 6 C's, 12 H's, 6 O's, and you're gonna get 180.2. So I'm going to divide by 180.2. That's going to give me 0.024 moles. Now I need my kilograms of solvent. Well, I have 25 milliliters. Well, 25 milliliters, I at least need to get grams. Well, I know it's 1 gram per milliliter, which means if I have 25 milliliters, I have 25 grams. 25 grams divided by 1,000, you've got 0.025. All we do now is divide. 0.024 moles divided by 0.025 kilograms, and we get a molality of 0.96. I'm going to use a little lowercase m for a molality. All right, we have 2 more examples here. I have an aqueous solution of hydrochloric acid that is 36% hydrochloric acid by mass. We need the mole fraction and the molality. So 36% of hydrochloric acid by mass. Okay, so that means then that if I have 100 grams, I would have 36 grams of HCl and I would have 64 grams of water. Because hydrochloric acid in an aqueous solution means water. So if I want a mole fraction, I have to put these both in moles, which means I divide by my molar masses. HCl has a molar mass of 36.4. and water is 18.02. So I get my mole numbers of 0.987 moles and 3.55 moles. Okay, my mole fraction again is going to be, and it wants the mole fraction of HCl, so I put the HCl on top, which is 0.987, divided by my total, which is the two added together, and we get a mole fraction of 0.22, or it's about 22% of the solution in terms of moles. Okay, not grams, moles. B is molality. Okay, well, molality, like we just did a second ago, is moles per kilogram. So I take my moles of my solute, which is the 0.987 moles, because HCl is a smaller one, so it's a solute, over kilograms of solvent. If I have 64 grams, that means that I have 0.064 kilograms. We just divide, and I'm going to get 15.4 molal. Last one. A solution with a density of 0.876 grams per milliliter has 5 grams of toluene and 225 grams of benzene. We want the molarity. Well, molarity is moles of solute over liters of solution. So I need a total here. Okay. Well, I want my moles of solute, which is going to be the smaller amount. So I get my 5 grams of toluene. Divide by my molar mass of toluene. We add up toluene, which is C7H8. And we're going to get 92 grams per mole. So I'm going to get an answer of 0.054 moles. Well, I need liters of solution. Okay, so I have to take 225 plus my 5, gives me 230. And it has a density of 0.876. Okay, so remember density is mass over volume. So if I want a volume, okay, I got to rearrange a little bit. Well, volume times density is mass. So that means then that volume is mass divided by density. I take that, divide by my density, 0.876 grams per milliliter, and we are going to get an answer of 262.6 milliliters. Well, it's moles per liter, which is going to be 0.2626 liters, and all I do is divide the red number by the green number here, and I'm going to get 0.21 molar.